So we're very happy that Gordon Royle agreed to speak in this international relay for us. Thank you very much. Gordon's from the University of Western Australia, and he'll talk about real chromatic rules of planar graphs. Thank you.
Okay, thanks, Anita. So I had no idea that this was going to be such a huge operation when I agreed to this talk. I'm feeling a little bit daunted now. As Anita pointed out, even though I'm technically representing Sydney, I'm actually physically located in Perth. So I'm about 4,000 kilometers from where I'm advertised to be from. Perth, many of you, almost none of you will have been to Perth. So it's a city of about 2 million people. It's on the banks of the Swan River and also on the Indian Ocean. And that's what it looks like. Here are some small interesting things from Perth. There are some quokkas, a little marsupial, some black swans, and then a little quiz question for you. 3 of today's combinatorics speakers actually come from Perth. So there's me, and there's 2 others who went to high school and university in Perth and have subsequently gone on elsewhere. So see if you can figure out who the other 2 are. So this is a talk about things related to coloring graphs. So just some terminology, which most of you will know already. So we have a graph, and the graph that I've drawn here on the left is planar. So it has no crossing edges. Every face is a triangle, and except for one, which is the outside face, the infinite face, which is a square. So this kind of graph is called a triangulation of a square. Now, I've colored it on the right here with 4 colors. So to be a proper coloring, the vertices at the ends of each edge must be differently colored. So if I take any edge at all and look at its 2 ends, I must see 2 different colors. So there's a green-blue edge and so on. Okay, then the chromatic number of a graph is just the minimum number of colors you need in order to make one of these proper colorings. And for the graph of the previous slide, we can see outlined here 4 vertices, each of which is adjacent to all of the other 3. And so this little portion of the graph tells us that we need at least 4 colors, and the coloring that I showed you on the previous slide shows that you can do it with 4 colors. And so the graph has chromatic number 4. Right, of course, this idea that a planar graph can be colored with 4 colors was one of the sort of original problems of graph theory, famously the 4-color conjecture from about 1852. Guthrie conjectured that any planar graph, so again, planar is critical here, can be properly colored using 4 colors. During the 20th century, this conjecture became the most famous problem in graph theory, consumed numerous academic careers. There are many academics, many good, even great academics, who spent their whole careers pursuing the proof of the 4-color conjecture, and accomplishing great work, even if they didn't actually solve the 4-color theorem. The 4-color conjecture drove the development of several subfields. There were many concepts that were introduced for the 4-color theorem that then subsequently became of independent interest. And then finally, the 4-color conjecture was proved by Appel and Harkin in 1976. And in those days, it was somewhat controversial because they used a computer to do a lot of case checking, and some people found that to be, well, you can see the quote on the left from the New York Times. One place that Appel and Harkin visited, the professors prevented them from meeting grad students in case their minds become contaminated. The controversy, of course, has died down nowadays, where more and more results rely on computation in some way or other. Okay, so today's talk is about a function called the chromatic polynomial. It was introduced in 1912 by Birkhoff, and his intention was, his hope was, to use the chromatic polynomial to prove the four-color theorem using essentially some analytic arguments. So the definition of the chromatic polynomial is that for a graph G and Q being a positive integer, then P sub G of Q is going to count the number of proper Q colorings of G. Now, there's no reason why this should be easy to compute or calculate, and in fact it isn't. But Birkhoff was basically hoping that by sort of solving the slightly more difficult problem of counting four colorings, he would at least be able to show that there were that there were more than one, not zero, four colorings of a planar graph. Okay, so the idea was he introduced this function. In his paper, he proved that it was a polynomial function of the number of Q, the argument, and then he was trying to sort of calculate it in some way for planar graphs. Okay, so Birkhoff showed that it actually is a polynomial. In practice, almost the only way we can calculate the chromatic polynomial for a general graph is by using the deletion contraction relation. So this expresses the chromatic polynomial of G as a difference of the chromatic polynomials of two smaller graphs, the graph with an edge E removed and the graph with the edge E contracted. And using that sort of relation, you can very quickly convince yourself that the chromatic polynomial is a monic polynomial of degree n. So if you have a graph of 20 vertices, then q to the 20 is going to be its leading term, and it has alternating coefficients. So, and again, for practical computation for general graphs, we really don't know anything better than to use some variant of the deletion contraction relation. Okay, so here's an example. There's a graph here on the left, 10 vertices. It's cubic. Every vertex has got 3 neighbors. And here's a polynomial. And basically, all we really need for the rest of this talk is sort of you just need to understand that for each graph, there is such a polynomial. And it's just some sort of ugly looking expression. The fact that it's got factors of q minus 1 and q minus 2 is because this graph has got no 1 colorings, and it's not bipartite, so it's got no 2 colorings, and it has no 0 colorings, of course. And then in general, the other term is just going to be some unpleasant looking polynomial. Again, the only sort of general thing we can say about it is that it's going to be have alternating coefficients. Over on the right, I've actually just plotted the polynomial itself. So there's no 0 colorings, no 1 colorings, no 2 colorings. Of course, there's lots of 3 colorings, and then this polynomial is going to rapidly head off towards infinity. Now, because it's a polynomial, we can actually just ask for what its roots are. And we can ask for either its complex roots, or its integer roots, or its real roots, and see what can be said in each of those cases. In this case, the polynomial's got real roots at 0, 1, and 2, and another one at 2.30369. we really can't say much about, well, anything really about the significance of, we can't talk about 2.30369 colorings of a graph. So for the moment, it just has to be sort of a curiosity as to what that might mean. Okay, I want to describe another way of counting the colorings of a graph. This is not a practical way of counting the colorings, but it's a way in which we can sort of theoretically calculate the chromatic polynomials for certain families of graphs in a relatively easy way. So let X be the set of all functions from the vertex set of G to the set 1 through Q. For now, Q is some fixed but arbitrary integer. So X is a set of every function. That means that some of these functions will actually be proper colorings, and the rest will just, maybe there's a function that assigns 1 to every vertex. Well, that's not going to be a proper coloring, but it's still a perfectly legitimate function. So X contains proper colorings and improper colorings. Now, let X sub E denote the functions or the colorings for which the edge E is monochromatic. So these are ones that are bad for E. They've colored E badly. So what we need to know then is if we could calculate the size of this set, the ones that are bad for one or more edges, and then subtract it from the total number of colorings, then we would achieve the total number of proper colorings. So total number of proper colorings then is going to be Q to the N, that's all of them, minus the size of the ones that are bad. Okay, but of course, a coloring that is bad for one edge might be bad for more edges. And so in order to calculate the size of this set, we have to use inclusion, exclusion, and we get the following expression for the chromatic polynomial. Okay, I'll explain what each of the pieces is. Okay, so for every subset of the edges, say A, I'm going to let C of A denote the number of connected components of the graph with all of the original vertices and just the edges of A. Okay, how many ways are there then in which every edge in A is bad, is monochromatic? Well, if every edge in A is monochromatic, then as soon as I have chosen a color for one particular vertex, then every other vertex in the same connected component is going to have to be assigned the same color. So that means essentially that I have C of A choices to make. Each component is then going to have all of its edges the same color. And so I've got Q independent choices. So putting together all of this using inclusion, exclusion just yields this sort of standard inclusion, exclusion expression. We will come back to this later. Okay, so what are the fundamental questions then? The fundamental questions for people who study chromatic polynomials and their roots is to find bounds on the location of the chromatic roots in terms of parameters or properties of the graph. The study seems to have fallen naturally into three sort of subfields. The integer roots, well, you're just asking about whether there are whether there is any coloring with a fixed number of colors. So that's just graph coloring. Well, when I say just, I mean, it's a huge topic, and we've already seen a couple of talks that have mentioned a lot about graph coloring, but from a chromatic polynomial perspective, it's out of scope. real roots, I'm going to talk about some things about real roots today. And then complex roots are interesting too, because these are very heavily studied by statistical physicists, because there is a deep fundamental relationship between the chromatic polynomial of a graph and the partition function of the Q-state Potts model. And so I'll just say some buzzwords so that if you're interested in that aspect, you can sort of look them up. So Yang-Lee theorems talk about phase transitions. Phase transitions occur at real limit points of complex roots. And so there's lots of work in statistical physics about the complex roots of chromatic polynomials. Here's a picture. So this is a picture of the chromatic roots, complex chromatic roots of all of the 9 vertex graphs. This is a picture of the complex plane. So I should have labeled it, of course. That's 0, and that's I, and that's 2i, and this is 1 and 2, and so on. Okay, so this is a picture that was sort of, I first saw a picture like this about 30 years ago, or 35 years ago, I guess, and was sort of intrigued by what I saw, and, you know, what does this all mean? Which are the extremal graphs? Why are there these holes in the picture, and so on and so forth? Okay, 2 major sort of long-standing open problems in the theory of chromatic roots were solved by Alan Sokal, and he showed 2 things. First of all, he showed that chromatic roots are dense in the complex plane. So the picture sort of suggests that there are holes somewhere, and there might be regions where the chromatic roots don't go. All of that sort of speculation was ruined by Alan, who just came along with one family of graphs, essentially one family of graphs, these generalized theta graphs. Here we've got theta 8, 3. We've got strings of length 8 joined together, and we've got 3 of them joined together. And he sort of showed that if you change 8 and 3 to other numbers, you can maneuver the roots any way you want onto the complex plane. He also showed that if you restrict the maximum degree of your graph, then the chromatic roots are bounded. In particular, he showed that if you take a circle of radius about 8 times the maximum degree, then all of your chromatic roots must lie in there. You can't have any chromatic roots sort of far flung. This 8 is certainly wrong. I mean, it's too big. The reason I say it's too big is because I know what the answer is, but I have no way of proving it. So, and this is a long time ago, I was staring at computer output, and I decided that, although it was sort of somewhat counterintuitive, that the complete bipartite graph, KDD, so just 2D vertices, so if, say D is 4, then that means it's just K44, a little 8 vertex graph. I reckon that graph has the chromatic root of maximum modulus over all graphs with maximum degree D. So take your favorite billion vertex graph with maximum degree 4, and K44 beats it. If this is true, then what this says is that, well, for degree 4, the maximum modulus is about 4.177, and that's about 1.044 times 4. And for degree 5, you get a slightly better multiplier, and degree 6 a better multiplier still. And if you let D tend to infinity, then some unpublished results of Alan and Jesus Salas tell us that it's about 1.6 times D. So the Allen's bound of 7.9 should really be 1.6, but we have no way of, well, I have no way of showing that. We don't like maximum degree anyway, because it seems like it's the wrong thing. You can take a couple of graphs, this green graph and this blue graph, and you can just glue them together at a vertex, and that way you can increase the maximum degree as much as you want, but you don't change any of the chromatic roots. So maybe if we knew what the right parameter was, we would be able to do more about bounding the roots. So this is a parameter that was suggested by Bill Jackson and Alan Sokol again. They called it lambda, capital lambda, and it's the maximum of, well, they called it the maximum flow between x and y. It's just the number of edge disjoint paths between x and y, which is, again, just the maximum flow in sort of the network flow sense. So if you take a couple of vertices, any two vertices, and you've got quite a lot of edge disjoint paths between them, then to some extent you've got sort of a dense, sort of a little dense region in your graph. And anything else you stick onto the graph is low connectivity rubbish that that doesn't really alter the roots of the chromatic polynomial. So really we want to replace maximum degree by this parameter lambda, and Alan and I managed to do it, but only for series parallel graphs, which is of course a tiny special case of graphs. In that case, we showed that lambda over log 2 was sort of a bound for the distance of any chromatic root from the point 1. Okay, so this just says that the region is not centered at the origin in this case, and this is about 1.4. Okay. Let's go to real roots. So again, the chromatic polynomial was defined for integers. There's no reason to put a real number into it, but there's nothing to stop you doing so either. Hayward, this is Combinatorics, he just showed that the number of 5 colorings is, every planar graph is 5 colorable. If we express that in chromatic polynomial terms, it just says that if you evaluate the chromatic polynomial at 5, you get something positive, but that's really cheating. It's got nothing to do with chromatic polynomials. It's just to do with coloring. Birkhoff and Lewis, on the other hand, said that if G is planar and X is any real number bigger than 5, then the chromatic polynomial is positive. They conjectured that this was true for X at least 4. So if you put any value into the chromatic polynomial of 4 onwards, then the chromatic polynomial is strictly positive. And of course, the motivation for this was to find a chromatic root-free interval for planar graphs containing q equals 4. So this would be sort of an extension of the 4-color theorem. This is still unsolved, and this was, again, so this is now 75 plus years old and still unsolved, which is a bit sad. Okay, let's look at root-free intervals then. So where do chromatic roots lie? And now I'm restricting purely to real roots. So 2 major contributors early on were Bill Jackson and Carsten Thomsen. Bill showed that there are no real chromatic roots in the regions -infinity to 0. Well, that's trivial. 0 to 1 is easy, and then 1 to this strange number 32 over 27. And Carsten Thomsen finished things off by showing that chromatic roots are dense from then onwards, forever onwards. Okay, but this is for general graphs, not for planar graphs, and so we haven't contradicted the the Birkhoff-Lewis conjecture. I've realized that I used the same picture as David did for Carsten Thomason. We must have taken it from the same Wikipedia page or something. What about planar chromatic roots? Well, the big name in planar chromatic roots, along with many other things, is Bill Tutt. He proved this rather amazing result, which is that, so phi is the golden ratio. If you take a planar triangulation, so now it's a planar graph where every face is a triangle, or maximal planar graph, then the value of the chromatic polynomial at phi plus 2, so just for reference, that's about 3.618, is, well, phi plus 2 times phi to the 3n minus 10 times, and this is positive because these are just values in, I mean, these just, you can just work out what that number is, times whatever the value of the chromatic polynomial was at phi plus 1 squared. Okay, as long as this isn't 0, then this will be positive as well. I'm going to explain shortly why it can't be 0, and then it must be positive. And this is Tutt's commentary on his paper. You know, sometimes people find it difficult to believe at first. So I think I found it difficult to believe at first because it seems astonishing that you should be able to do that. Okay, now phi plus 1 is not a chromatic root of any graph because its algebraic conjugate lies in 0, 1, which we already know is free of chromatic roots. So if you had phi plus 1, you'd have to have phi minus 1, but you can't. So for any planar triangulation, the value of the chromatic polynomial at phi plus 2 is strictly positive. Now, Thomas Perrott was a student of Carsten's. He looked at this in more depth in his thesis. I was hoping to lure him to Perth to work on chromatic roots, but he left academia and went to industry. But I just looked up his LinkedIn page a few days ago, and I suspect that he still sort of likes chromatic roots because that's his background, which we can recognize easily as essentially the same as that picture of chromatic roots of graphs of 9 vertices. Anyway, what did they show? They showed that if you can find a planar graph and the chromatic polynomial is negative for any interval, so let's just take, you know, so chromatic polynomial is doing its stuff. If it goes negative for an interval, then you can actually build graphs, enough graphs to find chromatic roots dense in that interval. So proving that chromatic roots are dense is hard because you need to find lots of graphs, but now they've reduced it to just finding a single planar graph that is negative over some interval, and then negativity implies density. Okay, so the Birkhoff-Lewis conjecture says that the region from 4 onwards should have no chromatic roots. And what we're trying to do now is fill in the region up to 4. And of course, the goal is to show that from 32 over 27 all the way up to 4, there are, you know, the planar chromatic roots are dense in that interval. Okay. For most points between 3 and 4, it's easy. You just search almost randomly and you can find, so here's a random planar graph and here's a region where it's negative. And so now we fill that in. We know that we can find planar graphs to make chromatic roots dense in that little region. And let's do another one. So anywhere that we find some planar chromatic polynomial going negative, we have solved the problem of proving that the planar chromatic roots are dense in that region. Right. So let's look at 3 to 4 then. So 3, 5 plus 2, and 4 are sort of special points. Well, first of all, the chromatic polynomial of a planar graph is always positive at 4. That's the 4-color theorem. And that means that the Perrott-Thomason technique won't work here. We also showed that the chromatic polynomial of a planar graph is always positive at 5 plus 2. And that means that their technique won't work there either. But everywhere else, it's fine. You can always easily find graphs with, planar graphs whose chromatic polynomial is negative from 3 all the way up to close to 5 plus 2, and then from close to 5 plus 2 from above up to close to 4. Okay, so what we're going to talk about now is how to fill in these gaps. Here's a picture of a lattice. This is an infinite triangular lattice. Well, it's not infinite at the moment, but imagine it going infinite. And what I've done is I've cut out a strip of this lattice of width 4, and I've wrapped it around a cylinder so that the left side connects to the right side. So this is a planar graph. Okay. Sami Baraha and Joseph Kahan found this family of graphs many years ago. In fact, just around the same time the 4-color theorem was being proved, and showed that it has complex chromatic roots arbitrarily close to 4. So they published a paper saying, is the 4-color conjecture almost false? It's like, if you put 4 into the chromatic polynomial, you get something positive, but you can't put anything in the complex plane arbitrarily close to 4. You can't guarantee that the chromatic polynomial is positive. Okay. Now, I discovered quite a few years ago that if I inserted into the top face, that top face is a 4 cycle, I'm going to put a triangulation of a square, just like the first graph that we found. It doesn't, this one doesn't work, but it's just an example. And I put a different triangulation of the square in the bottom face. So in other words, I glued some graphs onto the top face and the bottom face. Then I could push the complex roots arbitrarily close to 4, but push them onto the real line as well. Okay, so n graphs on a lattice, let the lattice get very large, and then I could find chromatic roots arbitrarily close to 4. Lattices are important for 2 reasons. First of all, these are the things that statistical physicists like to work with because they have, models of molecules on lattices interacting with each other and that sort of thing. So there's a huge literature in the statistical physics area of chromatic polynomials of large lattices. Okay. The second reason why lattices are interesting or useful is because we can actually compute their chromatic polynomials in a better way than just doing deletion contraction. It relies on the expression, the inclusion-exclusion expression for the chromatic polynomial that I presented before. So here's sort of the general idea. Every subset of the edges contributes to the chromatic polynomial and induces some partition of the boundary vertices. Okay, so this is the boundary, A, B, C, D. What I'm mentally imagining is I'm going to build more layers onto this. I'm going to extend this lattice and keep it going to very long. Okay, this particular edge set, the red edges, they contribute -1 to the 22 because there are 22 edges in that set, q to the 6 because there are 6 components. So let's have a look at the 6 components. One there, one there, one there, one there, and then the rest. Okay, so it induces the partition A is connected to D and B is connected to C and nothing else. What I want to do is I want to keep track of the total contribution associated with every boundary vertex partition. So all of the edge subsets that give me this particular boundary vertex partition, I'm just going to count them together and separate them from all the rest. Okay, why do I want to do that? The answer is that when I add a new layer to the lattice, so here I'm going to glue, this is the new layer coming on. It's going to, these two, it's going to eventually dock, and those two vertices are going to be, this, what looks like 8 vertices is just going to be 4 vertices. Now, I'm going to look at the subsets of edges. Now, any subset is going to be some new edges. These are the red ones, and then some old edges. But this graph down here is unknown and potentially large. However, I don't actually need to know all of the edge subsets of the sort of large unknown part of the graph. All I need to know is what their boundary partition was and what the total contribution to the chromatic polynomial was, because then the total contribution for all of the edge subsets for which these red edges are the new edges is determined purely by those particular edges and the boundary vertex partition that was, that the old edges induced. Okay, don't worry too much about that because it's sort of the basic. All I really want to say is that you can work out the next polynomial, the effect of adding an extra layer, just by keeping some additional information about the chromatic polynomial. Okay, so back to Perrott and Thomason. Perrott and Thomason's thesis, Perrott's thesis rather. So 4 is no longer a problem because my results from earlier do that. Perrott found graphs going up to, with roots going with negative intervals going up to 3.618, and then from 3.618 onwards. So this is the gap that we have to fill in. It's 0.0003246. So of course, you might well say, why do we care about filling in a gap of 0.003246? But that's pure maths for you. Okay, so I saw Thomas give his talk, I was in Europe for some reason. And when I got back, I thought, well, let's try the same trick. So Melissa Lee and I, Melissa's now in Auckland, we decided to look at the width 5 case. So instead of taking a width 4 lattice and sticking n graphs into it, I thought, well, let's take the width 5 case and stick n graphs in. And lo and behold, it was basically trivial. All I had to do was stick, all we had to do was stick a single vertex in one end, and that graph, that family of graphs, letting the length tend to infinity, has roots tending to 5 + 2 from beneath. Let me just briefly say how all of this, how we analyze these things. So skipping details, but it's based on those boundary vertex partitions I was talking about. We can always get an expression for the chromatic polynomial of a lattice or really any repeating structure by a vector expression or matrix expression of the following form. U transpose T to the n minus 1 V. Essentially, U contains the information about one end of the lattice. T is called the transfer matrix, and that encodes the effect of adding an extra layer to your lattice. And then V is the other end of the lattice, the other end graph. All of these things are expressions in Q. So these are vectors and matrices whose entries are expressions in Q. I won't say that. Okay. What happens to a vector expression or a matrix expression when you have a matrix going to a high power? Well, what always happens when you are thinking about high powers of matrices is you start to think about its spectral properties, namely its eigenvalues and eigenvectors. So everything that happens really depends on, depends on the eigenvalues, eigenvectors, and a few other little things. Okay, let's look at the triangular lattice of width 5. What do these expressions look like? Well, here's U transpose. It's just the transfer matrix in this case is only 2 by 2. You can do some tricks to reduce the number of the dimensions of the transfer matrix by using symmetry and things of that nature. So the 5 by n triangular lattice, U is this vector here, that's a row vector, V is this, and here's the transfer matrix T, which is a nasty matrix. If I add a single vertex into the center, then it changes, the 1, 0 becomes Q minus 5, 1. That's the only change that happens. Okay. Well, the matrix T's got 2 eigenvectors, V1 and V2, eigenvalues lambda 1 and lambda 2. So if I just express V as a linear combination of eigenvectors, and I then take T to a high power, then all that happens is that I end up with an expression with the leading eigenvalue to the power n minus 1, the second eigenvalue to the power n minus 1, and each of those multiplied by some value. And these are the amplitudes. Okay. This is what they look like for those of you who are curious. So alpha 1 is this expression here, some horrible expression in Q, horrible to us, but easy to Mathematica. And this is lambda 1. And you can just put Q equal 5 plus 2, and we discover that lambda 1 is bigger than 1, and lambda 2 is smaller than 1. So this expression then is basically dominated by this. That expression is going to dominate what happens when n gets large. Well, then we're done, because if I just put Q to be something slightly smaller than 5 plus 2, then alpha 1 becomes negative. So the chromatic polynomial is just alpha 1 times lambda 1 to the n minus 1. So that's bigger than 1 and positive. That's negative. Well, that means that the value of the chromatic polynomial is going to be negative. So the net result of all of this is that this family of graphs, the triangular lattice of width 5, is enough to find chromatic polynomials that are negative as close to 5 plus 2 as you want on the left-hand side. So there's the family, there's one of the graphs and its chromatic polynomial, and the end vertex, the single vertex end graph is vital. Okay. What about the next one? Now, I haven't been able to do this part yet. I know, again, I know what the answer is, but I can't actually fully prove it. Okay, so having done, so we start to look for other families. Yep.
It's about 5 minutes, including questions.
Okay. Oh, sorry. Okay. Thanks. Okay, so I want to find roots in 5 plus 2 and 5 plus 2, just to the right of 5 plus 2. Looking at one of Alan Sokol's papers, I find the graphs that I'm looking for. They're 10p times 70f, so that's a 700 vertex graph, but it has a root in the right, sort of exactly where I want. The only trouble is that the transfer matrix here is 51 by 51, and its entries are polynomials of degree up to 10. And I can't find any sort of analytic way of analyzing that. So I'm sure that this is correct, and I would very much like to be able to finish this tiny little thing off. But for the time being, I'm just going to have to say that I'm not quite done with proving that planar chromatic roots are dense in the interval 3, 4. Okay. Thank you.
Thank you very much. Anita. We have a few minutes left for questions, so feel free to unmute yourself or send your question in the chat and I can read it out. And let's go ahead. So are there any questions? So I missed it maybe at the end. What would be your plan to go from above to 5 plus 2?
Okay, so the width 10 lattice does it. So it's 10 wide and you just let it grow infinitely long. The only trouble is I can't prove that it does it.
Oh, I see.
Because I can't just look at, I can't just substitute in, 5 plus 2 minus or 5 plus 2 plus epsilon and get anything sensible. So there is a lot of work done on what happens to eigenvectors and eigenvalues when you replace a matrix by a matrix plus a slight perturbation. So you try to use continuity, but to use continuity, you need to have simple eigenvalues, and that's why I'm sort of stuck. So the second thing is to actually just find another family of graphs. Like there are lots of types of lattice, there are lots of n graphs you can play with, and so on.
Right, that's what Gordon. That's what I was wondering. If the width 10 one, it works, but you can't prove it. Do we know that the width 9 doesn't work, or width 8 or something?
No, anything could work. There's no, as far as I can see, I have no control over. Yeah, so it's just that when I was sort of trying to decide what to try, then looking at ones that I knew had roots close to 5 plus 2 seemed like a good idea.
Definitely, thank you.
Yeah, but it could be anything. I mean, you could have triangular lattice, you can have honeycomb lattices, you can have all sorts of things, square lattice.
There was a very quick question in the chat. Did you have any open problems? You want to say something quickly on the penultimate slide? Or
well, the open problems. Oh, there are lots of open problems with chromatic roots, but they get sort of a bit, I guess, technical or not technical, a bit niche, shall we say?
Yeah.
I mean, probably. This is the big open problem is the Birkhoff-Lewis conjecture, planar chromatic roots in the region 4, 5. So finishing off 3, 4 is sort of a consolation prize for not being able to do 4, 5. So 4, 5 is
Okay.
really the one that I'd like to do.
Yeah.
Yeah.
Well,
Well,
thanks very
and
much.
then, yeah. Okay. Thank you.
Well, thank you so much. Let's all unmute and give a round of applause. Thank you.